I'm Carolyn Alkire with the Northeast Fisheries Science Center, presenting a learning model approach to estimate the cost of ropeless fishing adoption by northeastern U.S. fishing vessels. I also identify some potential sources of funding for gear conversion. Ropeless gear reduces the threat of whale entanglement. It's currently used commercially in Canada and Australia, and most recently in South Africa's octopus fishery. There's a new opportunity for use in California's commercial Dungeness crab fishery, with 2020 regulations allowing ropeless and other alternate gear to reduce the risk of whale and sea turtle entanglement. Ropeless fishing continues to be tested in the US and Canada. Many ropeless fishing components being tested have been assembled in limited quantities as prototypes, and are therefore more expensive than they will be after orders and production ramp up. So the economic concept of a reduction in production cost with increases in total output is referred to as economies of scale. Graphic representations of this correlation between production cost or labor hours per unit and cumulative production have been described as learning curves or experience curves. The aeronautical engineer Theodore Wright is credited with developing the concept of the learning curve in the 1930s, and it's widely been used to estimate both cost and time reductions in many industries, including electronics, automotive, software, and energy production. Wright's mathematical model became known as the 80% learning curve because, according to that rule, cumulative average costs are reduced, on average, by 20%, which is 100 minus 80%, as the number of units produced is doubled. To demonstrate the model concept applied to ropeless fishing, the average cost of a deck box is estimated for 3 production levels, 100 to 2,000 units, and 4 initial deck unit costs, $3,000, $5,000, $7,000, and $9,000, assuming a 95% learning rate, which is the conservative end of the 90% to 95% range for electronics manufacturing. This rate implies that doubling production could result in a 5% reduction in the average price per unit over all units. So the green, or the top line here, corresponds to a deck unit with an initial cost of $9,000. If production is ramped up to 2,000 units, the average cost would be a little over $5,000 each, based on Wright's learning model. The cost of adopting ropeless fishing is calculated based on the estimated number of trap and pot fishing vessels in the northeastern United States and the number of end lines or buoy lines. These are from the National Marine Fisheries Service vertical line model developed by Industrial Economics. The initial cost of ropeless fishing components is based on those currently commercially available. Adoption costs are calculated separately for nearshore and offshore because the cost of ropeless fishing components designed for shallower nearshore waters currently differs from those designed for offshore waters. The cumulative average costs of components are estimated using Wright's model, assuming all vessels adopt the technology. Based on these data values, the cost for nearshore vessels would be an estimated $418 million, and for offshore vessels, about $24 million, with a fleet-wide adoption cost of $442 million. The average cost per nearshore vessel would be about $57,000 and $48,000 per offshore vessel. An alternative lower cost estimate can be calculated by assuming that operators fishing more than 5 traps per trawl use acoustic releases on one of 2 end lines per trawl rather than both. The cumulative average cost for deck boxes and releases would be slightly greater in this case. In this alternative, the cost for nearshore vessels would be an estimated $400 million, and for offshore, about $14 million. Fleet-wide adoption cost would total $414 million, which would be $28 million less than if releases were on all end lines. The average cost per nearshore vessel would be about $54,000 and $28,000 per offshore vessel. This illustrates total costs for nearshore and offshore vessels for both end-line alternatives, $442 million and $414 million total. And this compares average costs per vessel ranging from $57,000 near shore for releases on all end lines to $28,000 offshore for releases on one end line per trawl. In addition to the potential for Congress to designate funding for widespread implementation, there are two NOAA programs that could assist. NOAA has the authority to provide long-term fixed-rate loans for a range of fishery-related activities through the Fisheries Finance Program. The costs that can be covered by loans include fishing vessel reconstruction and acquiring vessel equipment. Vessel upgrades to reduce bycatch are specifically allowed. Up to 80% of the total eligible cost may be financed at an interest rate 2% above U.S. Treasury rates. The Capital Construction Funds allows the use of pre-tax dollars to construct, reconstruct, or acquire fishing vessels. Funds can be used to pay for vessel reconstruction costs and for fishing equipment that is attached to the vessel, such as the through-hull installation of an acoustic transducer for ropeless fishing. So there's precedent for funding programs to incentivize fishers to switch to gear that mitigates ocean mammal entanglements. These include the Maine Ground Line Exchange Program, also known as the Bottom Line Project. Funding from the National Marine Fisheries Service, administered by the Gulf of Maine Lobster Federation, provided nearly $3 million between 2006 and 2009 to partially offset the cost of replacing floating ground lines with sinking ground lines. There's also been community initiatives for the purchase of acoustic alarms, also known as pingers, for gill nets to warn harbor porpoises and other animals away from nets. This includes programs by the New Hampshire Coastal Economic Development Corporation and the Gloucester Fishing Community Preservation Fund, and others. On the West Coast, the state of California and conservation organization Oceana are funding the $2 million cost for commercial drift gillnet swordfish fishers to replace their nets with more selective and sustainable gear. The costs I presented are based on the adoption of ropeless fishing by the entire Northeastern fleet, with vessel and endline estimates. In the future, with information on the number of vessels fishing in areas where ropeless methods are most feasible and most likely, these costs can be refined using the learning model approach. In addition to affordability, implementation also relies on progress towards other challenges, such as gear location, discussed by other presenters. Thank you, and if you have any questions, please feel free to contact me.